Welcome to the chemistry crash course. Today we are going to discuss about two more few concepts and some questions. Okay. So, let me go for the one concept before the de Broglie's wave equation. So, the dual nature of the light. Dual nature means the light behaves as a both particle as well as wave. Okay. So, dual, why we are telling dual? Even it acts as a particle and sometimes it acts as a wave. So, in case of certain phenomenon called as reflection, refraction like this, in such a phenomenon the light acts as a wave, while in case of a photoelectric effect, black body radiation, the light acts as a particle. So, here the dual nature of the light indicates the light behaves as a both particle as well as wave. Okay. Let us go for the de Broglie's equation. So, de Broglie's equation, so it is associated with the wavelength of a particle which is moving with a velocity v and having the mass m. It is associated with the wavelength of a particle which is having the mass m and moving with a velocity v. How it is derived? See, according to Einstein's theory, we know that E is equal to mc square, that is the energy is equals to mass into the square of the velocity. And according to Planck's quantum theory, E is equals to h nu, E is equals to h nu. So, what happens? Both are energies. So, we are going to equate mc square term, that is mc square is equals to h nu. Since we know that nu is equals to c by lambda, before we discussed the characteristics of the wave, and during that time nu is the frequency, that formula can be given as c by lambda. So, C and C get cancelled, lambda is equals to h upon mc. While this c indicates the velocity of light, when we are applying this theory for the particle, so we are going to replace the c by the term v, that is the velocity of a particle. So, finally, we came to conclusion that lambda is equals to h upon mv is the de Broglie's equation. So, see here it is associated with the wavelength of a substance which is moving with the wavelength of a particle which is moving with a velocity v and having the mass m. So, lambda is equals to h upon mv is the de Broglie's equation. Okay. So, this is important, you need to know, and then here h is the Planck's constant whose value already you know it, and then m is the mass and v is the velocity. Clear? So, let us go for the one more concept, Heisenberg's uncertainty principle. So, according to this principle, we cannot able to find out the exact position and momentum of a particle simultaneously. The momentum as well as the position of the particle cannot be find out simultaneously. See here that mathematical expression is delta x, that is uncertainty in the position and the uncertainty in the momentum, delta x into delta p is greater than or equals to h upon 4 pi quantity. Okay. So, it is impossible to determine the exact position and momentum of an electron simultaneously, that is mathematically given as delta x into delta p, which is greater than or equals to h upon 4 pi, and p is the momentum which can also be p is equals to m into v. Okay, we know that p is equals to m into v. So, delta x instead of delta p I am going to replace that term as m into delta v. Okay. So, delta x into m into delta v which is greater than or equals to h upon 4 pi. So, these are the concepts which we need to know. One is the de Broglie's equation and one more is Heisenberg uncertainty principle. Okay. Let us go for the few examples. An electron from the excited H atom jumps from higher energy level n is equal to 6, 7, 8 to the ground state. It means the electron is excited and in the spectrum line the higher energy level n is equals to 6, n is equals to 7, n is equals to 8, all these are coming to the ground state. All the radiations from the above, those are coming to the ground state. Okay. So, what is the question? We need to, this results the emission of, it means in which region we are going to get that emissions. Okay. as you know, when n is equals to 1, when n is equals to 1, that is the ground state where you are going to get the which type of the waves you are going to get the UV, okay, that is ultraviolet, and the second energy level is visible, and third will go for the IR, okay. Like this if we go means you are going to get the answer as a UV. Clear? From the higher energy levels to it will jump to the lower energy level means you are going to get the answer as a UV, ultraviolet waves. Next, according to Bohr's atomic model, the angular momentum of an electron, very simple question, according to the Bohr's atomic model, the angular momentum of an electron, angular momentum is the MVR, okay. So, what are the options? MVR is equals to 2 pi upon NH, MV R square is equals to NH upon pi, and then MVR is equals to NH upon 2 phi, and then MVR is equal to 2 pi upon N into H. So, what is the, from while studying the Bohr's atomic model, we know that MVR is equals to always the angular momentum is integral multiple of H upon 2 pi quantity. Okay. So, the in this question the choice is that MVR is equals to NH upon 2 pi. So, this is the correct answer. Clear? So, next one. According to Bohr's theory, angular momentum for an electron in the fifth orbit, angular momentum of an electron in the fifth orbit they have asked. So, what we know that MVR is equals to NH upon 2 pi. Is it clear? NH upon 2 pi, and then this is the angular momentum. So, what is the question? We need to find out according to Bohr's theory, angular momentum of an electron in the fifth orbit. It means they have given the value of n. They have given the value of n. So, substitute that n value as phi h upon 2 phi, and then if you just look at that options, if it is there, phi u h upon 2 pi is not there, here pi h upon phi is there, 25 is there, 2 pi, but if we simplify means 2 ones are 2.5. So, what is the answer? 2.5 h upon phi. So, there is a option D. Okay. So, this is how we can solve all this problem which is based on our theoretical background. Okay. Let us will continue the class in the next session with some other problems. Okay. Welcome to the chemistry crash course. Today we are going to discuss about the some concept which are very important. So, let me go for the concept of probability of finding the electron, that is probability of picture of electron. Here we are going to discuss about Schrodinger wave equation. So, Schrodinger he incorporated the requirements of the de Broglie's wave equation and the Heisenberg's uncertainty principle, and he gave the mathematical equation which describes behavior of an electron, in an atom. Okay. So, that mathematical formula of the Schrodinger wave equation is H cap into psi is equals to E into psi. Okay, where H cap is the total energy operator, which is also called as Hamiltonian operator. Okay. And then here, as we are telling, it is the total energy. Total energy is the sum of the kinetic and potential energy. So, here H cap is equals to T cap plus V cap. It means here this will be the kinetic energy operator, and this V is the, that is V cap is the potential energy operator. Okay. So, this is the Schrodinger wave equation where the terms, here this indicates the total energy operator, and then this total energy operator is further sum of the kinetic energy operator and the potential energy operator. Clear? So, now this E, that is energy, and psi is the wave function of the system. Psi is the wave function of the system. And this Schrodinger wave equation can also be written in another format, that psi square delta square psi divided by delta x square plus delta square psi divided by delta y square, delta square psi divided by delta z square plus 8 pi square m divided by h square into E minus V into psi is equals to 0. And here when this equation is taken in terms of x, y, z space coordinates, in the x, y, z space coordinates we are taking the Schrodinger wave equation. During that time it takes the format of the mathematical expression in this way, or the mathematical equation in this way, where x, y, z are the 3 space coordinates, and here m is the mass of an electron, h, and then E is the energy, V is the potential energy, okay. And we can say that psi, that is psi is the amplitude which is the wave function of the system, that includes amplitude of a wave associated with an electron. Psi is the amplitude of a wave associated with an electron, and psi square is the intensity of electron at any point, and psi square is the maximum probability of finding the electron, where we can able to find maximum number of the electron. This is the significance of psi and psi square, which is the wave function. Psi indicates the amplitude of the wave and psi square is the intensity of electron at any point. It means the probability of finding the electron is maximum. Okay. So this is regarding the Schrodinger wave equation. And next let us go for the orbital concept. Orbital is the space, it is the region in the space in where the probability of finding the electron is maximum. It is the region in the space where we can maximum probability of finding the electron is maximum, that is what we called as orbital. Okay. And there are orbitals, s orbital, p orbital, d orbital, f orbital, you might be knowing all these orbitals. Let us go for the shapes of the orbital. So keep in mind that s orbital is always having the spherical shape. S orbital is always having the spherical shape. And then p orbital, it consisting of the further three categories, px, py, pz. So if the p orbital is oriented along the x axis, means that is the px orbital. Okay. If this p orbital is it is along with the y axis, means that will be the py. If it is along with the z axis, means that will be the pz. And the p orbital is having the shape dumbbell. It is having the shape of the dumbbell. If that orbital is it is located along the axis of the x axis, means that is px. If it is located on the y axis, means that is the py. If it is located on the z axis, means that will be the pz. Clear? So this is how we can draw the shapes of the px, py and pz. And then p orbital consisting of the three subdivision, that is px, py and pz. And the shape of the p orbital is dumbbell. Okay. And next let us go for the d orbital. Here, as you know, d orbital is further divided into 5 categories: dxy, dyz, dzx, dx square minus y square and dz square and dz square. Here the d orbitals are having the double dumbbell shape. See here, if you look at the diagrams, you are going to get the double dumbbells, not only dumbbell shape, it is a double dumbbell shape. Okay. Here it will be the dxy and here it is the dyz. Just look at the lobes arranged along the x. If it is arranged along the x and y, means that will be the xy. Like this, you are going to get the dyz, dzx and dx square minus y square. And finally one more is there, that is dz square. It will be like this. This is the dz square, which is having the double dumbbell shape. Okay. So this is how we can explain about the orbital and shapes of the orbital. Orbital is the region in the space where the maximum probability of finding the electron is available, and then there are 4 orbitals, s, p, d, f. S orbital is spherical in shape, p orbital is dumbbell in shape, d orbital is double dumbbell, and depends upon the orientation along the axis. Those are given the names like px, py, pz like this. Okay, and f orbital is complex. Its shape we are going to tell it as a complex shape. Okay. So, this is how we can explain about the Schrodinger wave equation as well as orbital and shapes of the orbital. Further few more concepts we are going to continue in our next class. Thank you. Let us come to the concept of quantum number. See here, quantum number is a very important concept. Quantum number means an electron of an atom is characterized by a set of 4 numbers. An electron of an atom is characterized by the set of 4 numbers. Those are called as quantum numbers. So, which are those 4 quantum numbers? Principal quantum number, azimuthal or subsidiary quantum number, and magnetic quantum number, and spin quantum number. So, an electron of an atom is characterized by a set of 4 numbers. Those are called as quantum numbers, and there are 4 types of the quantum numbers are there. So, let me explain one by one. First one is principal quantum number. So, principal quantum number is indicated by the letter n. Okay. And the principal quantum number, it tells about the main energy level or main energy cell. Even it tells about the size of orbital, even it tells about the size of orbital, and even it tells about the energy of the orbital. So, the principal quantum number is indicated by small n, which mainly refers or it indicates the main energy level or main energy cell, and also it determines the size of an orbital and energy of the orbital. And the value of the n is, n acts as an integer, the value of the n will be 1, 2, 3 and so on. Okay, like this. Suppose n is equals to 1, that is what we called as K shell. When n is equals to 2, that is what we called as L shell. N is equal to 3 means M shell, and 4 N shell, KLMN. Okay. Suppose n is, it indicates what? First orbit. Suppose this is the nucleus, this is the first one, this is n is equals to 1, that is the first orbital. It main energy level is indicated by the principal quantum number. So, let us go for the second one, azimuthal, or second one is azimuthal quantum number or subsidiary quantum number. Okay. So, it mainly tells about the subcell. It mainly tells about the subcell, and it indicates the shape of the orbital. Shape of the orbital. And the value of the azimuthal quantum number, that is L, depends upon the given value of the n. For a given value of n, L can take the values, L can take the values of, that is we can say 0 to n minus 1, 0 to, for a given value of n, L can take 0 to n minus 1. So, let me tell you how. So, first one, when n is equal to 1, when n is equal to 1, L is equals to 0. L is equals to 0. So, when L, that is subsidiary quantum number, is 0, it indicates S orbital or S subshell. Okay. And then for a given value of n, that is n is equals to 2, L value is 0 and 1, value of the L will be 0. And here if L is equal to 0 means that is yes, if L is equals to 1 means that will be 0 means s and 1 means p orbital, p orbital. Okay. And then if n is equals to 3, the value of the L will be 0, 1, 2. As n is 3, I am telling you, for a given value of n, L can have the value 0 to n minus 1. So, if n is equals to 1, L is equals to 0, it acts as a S subcell, and if n is equals to 2, L can take the two values 0 and 1, it indicates S and P. If n is equal to 3, L can take the three values 0, 1, 2, which indicates S, P, D orbitals. Okay. If n is equals to 4 means L is equals to 0, 1, 2, 3, that is S, P, D, F subcells. Clear? So, the azimuthal quantum number, or it is also called as subsidiary quantum number, which is indicated by a letter small l, and this value of the L depends upon the principal quantum number. For a given principal quantum number n, L can take the value 0 to n minus 1, and the importance of the azimuthal quantum number, it indicates the subcell and even it determines the shape of the orbital. Suppose the value of n is equals to 1 means L value will be 0 and it indicates the S orbital or S subcell. Clear? And then if it n is equals to 2 means L can take the two values. If n is equals to 3 means L can take the three values 0, 1, 2, and keep in mind that when L is equal to 0, that will be S, when L is equals to 1, that will be P, when L is equals to 2, that will be D, when L is equals to 3, that will be F. Clear? So, this is the second quantum number. Let us go for the third quantum number, that is magnetic quantum number. Magnetic quantum number indicates orientation of the orbital, in the space, and it is indicated by a letter small m. Then this magnetic quantum number depends upon the azimuthal quantum number. For a given value of L, m can take that is minus L0, minus L2 plus L value. So, how this can be taken, I will explain you. So, let me tell you, suppose when L is equals to 0, that time the magnetic quantum number m is also equals to 0. Then what does indicate, what is L is equal to 0 means which subcell? S. Okay. It indicates that S subcell has only one S orbital. S subcell has only one S orbital. Okay, suppose L is equals to 1. During that time, what is the value of m? I said you minus L, 0 and plus L. It means it can take the value of minus 1, 0, plus 1. When L is equals to 1, m can take the value of minus 1, 0, plus 1. So, now when L is equals to 1, which subcell it is? L is equal to 1 means that will be the P. It indicates that P subcell has 3 P orbitals. P subcell has 3 P orbitals. Which are those? Px, just now we discussed about the shapes of the orbital, Px, Py and Pz. So, these are the 3. Then let us go for the L is equals to 2. Might be you are guessing, when L is equals to 2, m is equals to minus 2, minus 1, 0, plus 1, plus 2. Okay. and L is equals to 2 means which subcell it is? D. See here, value of L, L 0, 1, 2, 3, 4, and here subcells are, here it is S, P, D, F, G, like this, okay. And then now we have L is equals to 2, L is equals to 2 is there, which orbital it will be? D subcell, okay, D subcell. It means what it indicates? D subcell has how many here? 1, 2, 3, 4, 5, 5 D orbitals, 5 D orbitals. Which are those? dxy, dyz, dzx, dx square minus y square, and dz square, and dz square. And one more thing, when L is equals to 3, that time M is equals to minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So, if L is equals to 3 means which subcell? F subcell has 7 F orbitals. F subcell has 7 F orbitals. Here one more time I am telling you, the quantum numbers are depends upon 1 and 1. See here, this azimuthal quantum number depends upon the principal quantum number, okay. And then next magnetic quantum number depends upon the azimuthal quantum number. So, if n is equals to 1, then L is equal to 0, it shows S subcell or S orbital, and if n is equal to 2, L can take the two values 0 and 1, it indicates S and P. If n is equal to 3, L can take three values 0, 1, 2, S, P, D. If n is equal to 4, L can take the four values 0, 1, 2, 3, S, P, D, F, like this. This L, that is subsidiary quantum number, depends upon the principal quantum number. So, when we go for the magnetic quantum number, that is M, it further depends upon the azimuthal quantum number L. How? If L is equal to 0, then M is equal to 0. It indicates what? S subcell has only S orbital, only one S orbital, there is no any further orbitals. If L is equal to 1 means M can take the three values minus 1, 0, plus 1. It means here 3. What these 3? These 3 are the 3 P orbitals, okay. Why I am taking P only? Because I know that when L is equal to 1 means that will be the P. When L is equal to 1 means that will be the P only, okay. So, the P subcell has a 3 P orbitals. Those, which are those 3? Px, Py, Pz. Similarly, if L is equal to 2 means M can have the minus 2 to plus 2 values, that is minus 2, minus 1, 0, plus 1, plus 2. Totally how many? 5. It indicates when L is equal to 2 means that is the D subcell. That D subcell has how many D orbitals? 5 D orbitals. 5 D orbitals. And then those are dxy, dyz, dzx, dx square minus y square, and dz square. And if I go for L is equal to 3, you are going to get the 7 values, and those 7 values are the indicates F subcell has 7 F orbitals. Clear? So, this is how we can explain the third quantum number, and next one is spin quantum number. Spin quantum number. Spin quantum number is indicated by S. It indicates the spinning orientation of an electron, whether the electron will going to be rotate clockwise or anti-clockwise, okay. That S value can be given plus half or S can be given as minus half, and it indicates clockwise and anti-clockwise orientation. Anti-clockwise orientation. And while we are writing, that is symbolical representation, we are going to use like this, clockwise, anti-clockwise, like this we are going to use. So, this is how we can explain the 4 quantum numbers. Clear? So, principal quantum number, azimuthal or subsidiary quantum number, magnetic quantum number and spin quantum number. So, briefly I will explain all these in one diagram. This is our nucleus, this is our nucleus, and then these are the energy levels. See here, I will roughly I will see. Okay. So, nucleus here, this will be n is equals to 1, n is equals to 1. Here it is n is equals to 2, n is equals to 3, n is equals to 4. And then this is a K shell, this is the L shell, this is the M shell, this is the N shell. Are you getting? So, now I need to calculate how many electrons are accumulated in the K cell, how many electrons. That can be calculated by one formula 2n square, that can be calculated by one formula 2n square. So, here n is equals to 1, first orbital, that is K, 2n square, that is 2 electrons can able to accumulate, 2 electrons can able to accumulate here. Okay, when n is equals to 2, that will be which L cell, then substitute in 2n square, how many? 8 electrons. In the second, 8 electrons are there. It means in the first orbital S can able to accumulate, S orbital is there, S orbital, and the capacity of the S orbital is only to accumulate with the 2 electrons, with the 2 electrons, and here 2 electrons, that is first orbit is there, that will be acts as 1s, that will be acts as 1s, and here 8 electrons means it includes S and P, it includes S and P. P capacity of P is 6 electron, it means it is the second orbital, it will be 2s and 2p, it will be 2s and 2p. Similarly, if I go for n is equal to 3, M cell and 2n square, 18 electrons, it includes S, P, D, it means 3s, 3p and 3d, and the capacity of the d orbital is 10 electron. And finally, when n is equal to 4, that is n, 2n square, that will be 32 electrons, that will be S, P, D, F, that is 4s, 4p, 4d and 4f, and the capacity of the F is 14 electrons. Okay. So, for S can able to accumulate 2 electrons, that is why we will write 1s2 like this, 2s2. Why we are writing only 2? S can able to have the 2 electrons. For P, 6 electrons, and then for D, 10 electrons, and then for F, 14 electrons can able to accumulate for the F. So, like this we can explain the electron distribution in the S, P, D, F orbitals. Clear? So, we will continue further concept in our next class. Thank you.